Hi, today we will present the Bayesian decision theory. So let's start with the Bayes formula. So going back in reviewing some basic statistical concepts, we are talking about random experiment when we are talking about an experiment for which the outcome cannot be predicted in advance with certainty. So that experiment has different possible outcomes, and we define as the sample space the set of all these possible outcomes or results of an experiment. So that sample space can be either discrete, so we have a finite set of possible outcomes, or continuous when the outcomes are not enumerable. And from that, we get into what we call a random event. So the event is the result of a random experiment. So we are getting a result of a random experiment. This result is a subset of the sample space. So we can define a random event as some part of the sample space that we are looking more carefully. And from that, we can evaluate the probability of getting that random event. So we get a real number that is representing the application of a given event related to a random experiment. So we have an experiment, and we are looking at the probability that the outcome of that experiment will be event A. And that event A is part of the sample space. And this number, this probability, is satisfying the axioms of probability. That is, the value is between 0 and 1 for any possible event A. If we are looking at the probability of getting an outcome in the sample space, that probability is 1. It means that the sample space describes all possible outcomes. So when we are making an experiment, when we have a random experiment, necessarily the outcome will be within the sample space. So we have a probability of U equal to 1. And also, if we are looking at some events, AI says I from 1 to N, and we are assuming that these events are mutually exclusive, such that there are no overlaps between the events. Then the probability of getting some as outcome one of the possible events is equal to the sum of individual probabilities of each event. So if we see that there are no overlap between all the events that we are considering, then the probability of getting one of these events is the sum of getting each event individually. So if we have 3 possible events, A1, A2, A3, the probability of getting one of these 3 events, if they are mutually exclusive, is equal to probability of getting A1 plus probability of getting A2 plus probability of getting A3. Let's get the example of tossing a coin. So in that case, the sample space is equal to either tail or head. We assume that these are the 2 possible outcomes. Then we can look at a given random variable X, which is either 0 and 1. So we are using 0 and 1 because it is simplifying the developments. And we assume here that the 0 is equal to a head and 1 is equal to a tail. And from that, we can use a Bernoulli distribution to model this. So this gives us as probability of X, small x, the event being, so the one outcome being in the event X. We are saying that it is following a Bernoulli distribution such that this is equivalent to getting a probability equal to 1 minus P1. P1 is the parameter of the Bernoulli distribution, which correspond to the probability of getting a tail. So this is 1 minus P1 power 1 minus X, where X is the outcome here that we care, times P1 power X. So if we have a set of samples according to a probability distribution parameterized by P1, so we have n samples, n different samples. They are making the set big X in bold here. So we have this set here defined as xt, so x1, x2, x3, up to xn. And these are all, I would say, yes, they are drawn according to this Bernoulli distribution. We can then say, okay, we will estimate P1 by sampling. So we will generate we have these n samples, and we want to know what is the P1 underneath that is producing these samples, these outcomes, and we see that P1 hat here is equal to the total number of tails that we have in our sequence divided by the size of that sequence and number of tosses. So we know that we have n tosses, and we will sum, in fact, the xt from 1 to n. And this will give us a number of tails because we are modeling this as a 0, 1 value. So if we have a head, it is equal to 0. So nothing is counted here. And if we have a tail, it is counted as 1. So summing this will give us precisely the number of tails that we have in our set of samples. And then if we want to estimate to run the prediction on the next test, which we call x index n plus 1, we can simply predict it as a tail if we know that P1 hat is higher than 0.5. Otherwise, it is head. If it is equal to 0.5, it is random. We could just say head, which is a default prediction. But if it is below 0.5, it is more likely to be a head than a tail. As example here, we see that we toss the coin 9 times, and then we've got this set of 9 samples here. So we see this, we have in fact 6 tails and 3 heads, and we can estimate the probability P1 hat as the sum of xt. So basically we will get 6 tails over 9 tosses. And this gives us a P at 1 equal to 0.66667 or 2/3. Let's get into the example of credit risk assignment. So here we get back to the example we had last week of having as input data x1 and x2. x1 is the income and x2 is the amount of savings. And from that, we want to estimate whether an individual is at high risk of default. So with C equal to 1, it means that this is an individual that is likely not be able to reimburse the credit, versus C equal to 0, which is an individual at low risk of default. So if we are able to get the probability of C given x1 and x2, so here the vertical bar is really a given that. So given that we have x1, x2, what is the probability of being C equal to 1, like here? So the probability that an individual is at high risk, given x1 and x2, if that probability is higher than 0.5, we can simply assume that this individual is at high risk. So we will assign this individual as an high risk individual. So we go from the probability up to a decision here, based simply on the fact that we get the most likely label according the label that is made according to the highest probability. We have 2 choices. So if it is not the first case, then it is necessarily a case of low risk individual with C equal to 0 here. We can get into an equivalent formulation simply by stating that instead of looking at 0.5, we will just look at the probability of C equal to 1 is higher than the probability of C equal to 0, given the same x1 and x2. So if we see that the probability of C equal to C1 is higher than probability of C equal to 0, we assign the individual as an high risk individual with C equal to 1. Otherwise, it is a low risk individual with C equal to 0. This leads us to the notion of conditional probability. So here, P of E given F. So we have P probability of getting that the event E will occur given that we have the event F that has occurred. We can simply say that this is equivalent to getting probability of getting E and F. So this is the intersection. What is the probability of getting both of these events divided by the probability of getting F whatever E? So if we don't look at E, this is the probability of getting F. So we get this ratio as the conditional probability of getting E given F. Since this intersection operator is commutative, we can simply say that P of E intersection F is equivalent to P of E given F times P of F, which is also equivalent to P of F given E. All we get here, basically for the left part here, we just get this on the other side. So this gives us this thing times that thing. For this part here, we get into the fact that P of E intersection F is equal to P of F intersection E, which is equivalent to P of F given E times P of F. So we again move P of E, sorry. So we again move this here, but we exchange E and F to get this thing. So this gives us this equivalence, this equal to that. And so the base formula here is basically taking this, getting that part on the other side. So we are dividing by E. This gives us to the base formula here. So P of F given E is equal to P of E given F times P of F divided by P of E. Another way to look at this is to rely on that Venn diagram. So basically, we are looking again at the base formula. We say that, okay, the probability of getting E and F, which is that space here. How do we get it? Simply, we just first look at, okay, for that part, what is the probability of getting F here, which is that thing? So this is the whole space of that circle. And then we say, okay, what is the probability of being in that whole space and also being, so given that we are in F, what is the probability of being in E? So we say, okay, given that we are in F, what is now the probability of also being in E, which is basically that space here. So basically we say, okay, we are in F, but what is the probability of being in E given that we are in F? This is that. And this is P of E intersection F. Likewise, if we look at this thing here, what is the probability of getting F intersection E? Let's first look at the probability of being in E here. This is that region. And then we are looking at the probability of being in F given that we are in E. So this is that thing here. So basically, this is that. And this is P of E intersection F or P of F intersection E. So this is how we get into that formulation. And from that, we just move P of F or P of E, the other side as a denominator. And we fall on the Bayes formula. So in terms of classification, we are usually presenting the Bayes formula that way. So we have here the equation. We start with the prior probability P of C. So this is the probability of observing an instance of class C. We call this the prior, which is that component here. So whatever the X, if we just pick one sample in the data set, what is the probability of getting a sample from class C? C equal to 1, C equal to 0, something like this. Over that prior, we also have the class likelihood. So the likelihood here, it is not a probability. It is a likelihood. So it is not bounded at 1. It is in fact, likelihood is a function that describes the distribution of some data, and the integration over the domain is equal to 1. So the likelihood here is the likelihood that an observation of class C is X. So we say, okay, we have a sample from class C. What is the likelihood of getting that specific X? So we are looking at the X itself. And the evidence is simply the likelihood of observing data X. Some data may be more rare than others. So whatever the class, what is the likelihood of picking up a given X in our data set? This gives us the evidence, and from that we are applying Bayes and we get the posterior probability. So the posterior probability here is the probability that an observation X belongs to the class C. So let's say we are observing X, then what is the probability that X is coming from C equal to 1, C equal to 0 among the possible outcomes? So if we are looking at this, first, if we assume that there are two possible classes, C equal to 0, C equal to 1, these are the only two outcomes, then the sum of probability of getting something from class 0 plus getting something from class 1 is equal to 1. So P of C equal to 0 plus C equal to 1 is equal to 1 because there are no other classes. Then we are looking at the posterior probabilities. So given X, the X is coming either from C equal to 0 or C equal to 1. So the sum of probabilities of the posteriors is also equal to 1. It cannot come from something else. So this is equal to 1. And the evidence here is evaluated in general by looking at the prior time the posterior, time the likelihood. So we have the prior of being of class 1 and the likelihood that X is coming from class 1, and the same thing for class 0. So by summing this, we are getting it at the evidence. So the likelihood of getting sample X, whatever the class. An example of this is to say, okay, we are looking for vehicles, we are observing vehicles, and there is two possible outcomes. This is either a car or another type of vehicle. So let's assume that the priors here is that 70% of the time, so 0.7 is the probability of observing a car of P with C equal to 1. And then the other case is observing another vehicle is 0.30%. So this is P of C equal to 0. So these are the two possible outcomes. So these are the priors of our example. Then we are observing a given vehicle. So we have a given X, and then that X, from that X, we get the likelihood of the observation. So the likelihood that X is from C, so assuming that it is from class 1, the likelihood is 1.1. So it seems that, okay, what is the likelihood of getting that X if we are from class 1? This is 1.1. And likewise, if we assume that this is coming from class 0, what is the likelihood of getting that X? It is 0.4. You can see here that the likelihoods are not bounded at 1. The likelihood can be between 0 and infinity, but it is integrating at 1. And here, the sum also of the likelihoods is not equal to 1 or something else. There is no limits on that. And then if we are looking at the evidence here, we are looking at the likelihood of getting X assuming C class 1 times the probability of getting a sample from class 1 plus the likelihood of getting X given assuming it is from class 0 times the prior of class 0. This gives us the evidence Px. And we just put the numbers here. So we've got as likelihood of class 1, 1.1. We have the prior of class 1, 0.7, plus the likelihood of class 0, which is 0.4, and the prior of class 0, which is 0.3. And we get as final values, final evidence, 0.89. So 0.89 is the evidence of observing X. From that, we get something really interesting in terms of classification. We are able to get the posterior probabilities, which can be used then for making a decision. So what is the probability that given the observation X is coming from class 1? So we are applying base here, and then we have the prior times the likelihood divided by the evidence. We're just plugging in the numbers. So we got 0.7 here, we got 1.1 here, and we have 0.89 here. This gives us 0.865. So we have 86.5% as probability that X is coming from class 1. And similarly, we are doing this for class 0. So give us 0.134. And if we are summing these two probabilities, it is summing to not exactly 1, because we are kind of stopping at 3 numbers after the period. But if we got more numbers after the point, we will get something equal to 1.0.